Welcome to the CompTIA Network Plus N10 008. This is Chapter 6, TCP/IP Basics. There's quite a few objectives in this chapter, so let's take a look at them. 1.1 Compare and contrast the Open Systems Interconnect OSI module layers and encapsulation concepts. 1.2 Explain the characteristics of network topologies and network types. 1.4 Given a scenario, configure a subnet and use appropriate IP addressing schemes. 1.5 Explain common ports and protocols, their applications, and encrypted alternatives. 1.6 Explain the use and purpose of network services. 2.3 Given a scenario, configure and deploy common Ethernet switching features. 4.2 Compare and contrast common types of attacks. 5.5 Given a scenario, troubleshoot general networking issues. When we start thinking about the network layer, we have to think about the types of data going across the network layers. So for example, IPv4 addresses, IPv6 addresses, and then you will see ICMP or different echoes on the network to communicate, like ping if it's on or off. Okay, so we have an example of a header in green. Let me get my little pointer. So the very first part of the header, you'll see the version. And then on the right side here, we'll talk about these other ones. Total length. So it's the total size of the packet in octets. Okay, time to live. So time to live gives you how much time that it will use for a packet to go through a router. So the numbers will usually be around 255 or maybe 128. I just remember seeing like 250, 255 more, 200. Okay, protocol. So different protocols are used to communicate to different computers for different reasons, and you'll see the protocol at the end of the header. Okay, so let's talk about TCP and how it's a bit different from UDP. Take a look at the computers on the left here. We have a client and we have a server. So when a client begins a connection, it tries to synchronize with the server. And the server synchronizes and it acknowledges that it synchronizes and it sends that packet back. And finally, the client acknowledges the sync has happened. So this is called a sync-ACK, three-way handshake. And that is how TCP connections become in a state. If you take a look here, I did a netstat command to see the active connections on my computer. You can see that they're in different states here. So there's a sync that has been sent, there's been an established connection, and there's one that's closed. So there's our three different states here that you can see for TCP/IP. Okay, here's an example of a TCP/IP packet and what it would contain. So you would need to know the source port, destination port, the sequence number, and acknowledgement number, because of course it's being acknowledged. But if we look down here, this is a UDP packet. And how different is a UDP packet? Well, it doesn't really have to synchronize. It just, as soon as it gets a request, it gets the connection, and it doesn't have to acknowledge it back. So that's why there's not an acknowledgement number here. Okay, so we've been talking a lot about TCP over IP, and of course we already know media access control or MAC addresses, which were popular before IP packets were. And we often have to use them together. So there's different encapsulation, switching, and routing that happens, and the packets will change depending on where they're going. So here's an example of an Ethernet frame with the MAC for the destination, the source. You can see the type of the data it is, like IPv4 or IPv6. And then here we have an IPv packet, the destination IP of where it's going, the source IP data, and whatnot. Okay, and I thought this little cartoon was really fun. So if a computer wants to know who is who on a network, what exactly happens? So there's different requests that go to the routing table. We'll get into that in a second, but here's a little cartoon first. Let's read it. I have its IP address, but what is its MAC address? So if we have one but not the other, how do we figure it out? Okay, that's computer A wanting to know this. Computer B is that computer that we're talking to, and we need to get this MAC address. So we're going to send a request. Who has the address 45? Please tell 23. And then, okay, now I'm going to send this info back to 23. Hey, I'm 45, and this is my MAC address 49. That is visually what's happening when you use an ARP, or address resolution protocol. So at a local level, we would resolve IP addresses to MAC addresses. Instead of really routing it in different ways or moving it to a different switch, we can just see what's on our local switch or our local routing table by doing this command on your computer. Okay, so that's enough of MAC addresses and IPs and ARP. Moving on. We'll need to know how to read binary. Binary is very important. Binary is so important, it's part of this Network Plus exam where we need to be able to possibly translate IP addresses into binary, vice versa, subnet, and there's other benefits for you learning binary as well. Okay, so let's take a look at this chart down here. So we have a 0, the first digit, a 1, and then a 2 would be the second place. And then a 3 is a 1, 1, and so forth until we start to see a pattern, right? So that's how binary works. Computers see addresses like this. They don't see 192.168.1.1. They would just see 11000001.001. They can calculate this much faster than we can speak. So it's quite snappy. On a side note, you also need to be aware of calculators. There's different programming features in calculators, and they'll give you binary if you don't want to do it in your head. You can be lazy and use a calculator. Okay, so we just discussed how to do some really basic binary to get some small numbers. But what about bigger numbers? Here's a real-life example of a home network or a SOHO, small office, home office. A lot of routers out of the box will use a 192 address. I believe mine does as well. I'm on like a .12 or something. So let's take this example here. In order to calculate a class C or a larger number, maybe class B as well, we need to use division. I really like to use this method to do the higher numbers. So we're going to start with number 128 because that's the last digit in the octet of 8 numbers. So start with 128 and half it. So half of that is 64. What is half of 64? It's 32. What's half of 32? 16, and then half, 8, half, until you get 1. So I always write 128 and half it on my scratch paper for the Network Plus exam. And then that way, if you do see an octet like this, it's quite easy for you to configure it. So the very last number here, if you see a 1, it means 128. So 128, and then the next number here is 64. So 128 plus 64 is 192. So 192.168.0. It's a good idea to familiarize yourself with that so you can really catch that and know if it's a class C or not. I bet they're going to trick you a lot, and it's going to look similar but not quite, and you'll have to know the exact answer to get the correct score, to get a good point. Okay, moving on to a more realistic one. Here is a network private address. We got 202. Okay, so you're going to run into network IDs and different subnets and LANs that are not 192 or not .10 or not .172 or whatever. So this one is less standard, and that's fine. Go outside of your comfort zone. Do something different, right? So go ahead and pause the video and try to do this by yourself. Can you get the correct answer? Okay, so the very first octet, write out 128 and go down, right? Like we mentioned earlier. So the very first number here, I'm going to do 128. Okay, 6, 4. We're going to skip two numbers. Skip 32. Skip 16. Okay, now we have 8. We're going to skip 4. We're going to include 2. And then, okay, we don't have a 1 there. So that comes out to 202. Did you get that for the very first octet? Okay, so use that method. Write out the ones and zeros that way from left to right. And then start with the higher number. So the next one we have is 120. Okay, so what are we going to write out? Pause the video, think about it, do it by yourself, take this seriously, start practicing it and do it. What did you get? Okay, so if I have 64 followed by 32, 16, and 8, that comes out to 120. So a little bit of division, a little bit of addition, but that's it. Don't get too overwhelmed with this. You don't need to know too much math. It's not too crazy. Okay, in the next one we have a 10. That's how you write out 10. We have number 8 and number 10. And notice here, I actually went from right to left. I didn't go left to right. Why did I do that? Because it's a smaller number. You don't have to start out so high. So here I have number 2. Okay, skip this, 4. Next one's 8. So I went from left to right to get that smaller one. And then the very last one I did 4, 2. Try to do these other ones as well for extra practice and see what it comes out to. How do you feel now? Do you feel a little bit better? Do you feel confident? Hopefully you don't feel like you're entering the matrix or doing something crazy or complex. It really does give you a good idea to understand the default subnet mask. Can't talk, because usually when it's all ones it's 255 like that. So that's all it is. Understanding what's available, how many hosts you have on the right and what's the mask on the left gives you much better visualization of network IDs, subnets, and gateways and why it's built that way. Okay, so we talked about binary and numbers. We talked a little bit about subnet mask and why that's important. We're going to do more exercises about them in a bit, but before we do that, let's talk about routing. How does a packet get from inside a LAN in a private network out to the internet in a public network, or vice versa? So the answer to that is routing, or routing tables. So the routing table is going to point where packets go on a network. So here, if I have a routing table with this rule, if I have a packet that's going to .1 on the LAN, which would, I guess, be the gateway or the router. Okay, so everything for this network ID 0 is going out of .1, which is our default gateway. So everything inside the LAN, that's a 202, because this is 202, that's a 202, that's a 202. They all are 202. So if it's inside this network ID, if it's inside this gateway, it's going to stay inside here and go in this host. That's what it tells you to. Everything else goes out to this address. This address is our ISP, our public IP, the internet. So if you have something that's routing to a website that's out here, it'll see this and it'll go to the correct route. Okay, great. So that's basically how the internet works. How can you get your private network at home to talk to the public networks outside? Your LAN to WAN connection. So local area network and wide area network, two different things. There's translation to get them to work together. There's routing tables to get them to work together. And we'll talk more about that. Okay, so we already learned binary. This is a binary string you're going to see a lot as a network technician. So if I fill up all the binaries and there's nothing left, what number is that? That would be 255. 255 is generally reserved for the broadcast address, and 0 is reserved for the network ID. So you can't really use those addresses because they're reserved. Okay. So this is a pretty typical subnet mask you're going to see on a default network that's not really configured. A class C network like a 192.168, and then we're going to have this last part is all 0. This is going to be reserved for our hosts, our computers. So maybe I have two separate LANs, two different switches or something, but it's on the same subnet mask. So this LAN can talk to this LAN. And how does it know it's in the same private network? Well, because of the mask. Okay, let's get a better example. Here's a classic Class C, a 192.168, like we were looking at earlier. Okay, we've already done that math. I'm not going to make you do it again. You already know it. Okay, here's a subnet mask that's pretty standard, 255, so it's all 111, 111, 111, 8 of those each in 3 different octets, 0 on the last octet. Here's a network ID. As I mentioned earlier, it's always going to end in 0. Broadcasts always end in 255. Okay, and the host ID. Okay, maybe your host has it could be some other number. It could be maybe .2, .3, it could be 20, it could be 40, 50, it could be 100. It depends on the scope of your network and how you designed it. Okay. So now you can see binary in action. We're really seeing IP address. We're seeing binary number and putting it on paper. Great. Moving on. How do computers think, though? Okay, so these are for quick reference of subnet masks that you're going to commonly see because 255 is just the default. You can obviously change that if you want to, but get used to seeing this and know exactly how many there are. How many ones are there? If these are octets, 1, 2, 3, 3 times 8, 24. So then we call that a CIDR 24, or some people even say a /24. That's why there's 24 ones. Okay, what about this? How many ones are there? We call that a CIDR 16 network. How about this one? A CIDR 8 network. So basically a Class C network would work here better, a Class B network would work here better, and Class A network would work better there. So knowing what class you're using, you can assign how many hosts you want in that network to talk to each other. So having a Class A network, you're going to be on a much bigger environment probably. Thousands of connections going on. Class B, less than that, and it'll give you more flexibility. You can subnet more. Here you can subnet even less on a 192. You have less hosts available per subnet. So depending on your needs of the network and what you're designing, you really have to be mindful and think and plan ahead and always have room for growth and improvement. Okay, So I already talked about classful subnets, what CIDR notations are, a block 8, a block 16, block 24. So you can understand that way. If I say it's a block 25, then you know there's going to be 25 of them. Okay, I want to talk about this method of using exponents. So let's take any number that you want. For example, let's use a CIDR 16 subnet mask. So we're going to take the exponent of 16, 2, 16 minus itself. So really it's just 15. 2 to the 15th power means you got 65,534 total hosts. So in case you don't want to memorize the exact number per CIDR, you can just memorize this formula. And that's a pretty good tool that you're going to need, and it's going to be handy when you need to know how many hosts are available on a network or how you're going to design it. So that's a great trick. Okay, so now we've got 16 ones. What if we move the subnet mask all the way to the right? We almost fill it up and we do a 26. Well, if you only have 6 ones available and you take that to the 5th power, that's only 62 total hosts. That's not that big. I hope it's a very small network, and if they need to grow, you're going to need to fix that. Okay, we saw this earlier in the presentation of what a general subnet mask looks like. Filled of ones, right? And it's probably 255 for 3 octets. And here's the last octet with available hosts. So default subnet mask and hosts. If I were to write this out, this is what? This would be a CIDR 25. Yeah, 3 times 8, 24, plus 1, 25. This would be my subnet mask. So we have different methods to configure our binary. Hopefully it's quick now. You know 128 is this number and you can half it down. Shouldn't take too long to visually inspect that and see that once you practice more and more. Okay, so here let's take an example where we need to make 3 subnets for a client. We want to divide the network in 3 segments. Okay, you have to pull 2 subnets at a time. Why do you have to pull 2 subnets at a time? Well, it could either be a 0 or a 1, so it's 2 per binary. Okay, so let's take this example of this network ID. It's a class C 192.168.4.0 on a 24 CIDR block. Translates to this binary. Okay, I won't pain you to do all of that, but we just know that this is the 0 here. Okay, so starting on this octet, 1, 2, 3, 4, 5, 6, 7, 8, we can remove this part of the binary, move it over, so now there's less hosts available, but we can pull these 3 that we need to make a subnet mask. However, we have 4 examples here. Well, welcome to subnetting. Everything is done in powers of 2, right? We've been thinking in that last slide, we saw 2. Now we're thinking more like a computer, like exponents. So we actually have 4 available subnets, and we're going to use 3. Okay, so you can pull from these ranges. If you want to divide it by 4, if you want to break up this particular available mask and divide it by 4, right? So in this available block, we know that from dot 1 to dot 254 is available pool of addresses, right? So that's over 250 addresses, and we can kind of segment it however we want to. We will segment it this way. We got to pick 3 of these, right? It can be any 3. You can pick this one and then this one and this one, or you can do the first 3 or the last 3. It doesn't matter. But okay, let's start with this one. So on a block 26, starting at 0, we're going to use a range from 1 to 62. So that's an available address there for that segment. Okay, moving on. Keep in mind the broadcast is going to be 63, so that's not available. 64 is now the network ID. It doesn't always have to be 0. It can start at 64. So then 65 is going to be client to 126, and the broadcast is going to be 127. So these are not available for you to use, and that's why that's 128, 29 to 190, and that's 191. So that's how network IDs work. They take an address away from you. Broadcast address take one address away from you. That's 2, 1, and 0, right? And then you have the available addresses for you to use. Okay, using this example, we see this coffee shop that has different segmentations, 3 different networks. So we decided to use the .0, the .64, and the .128 as our host IDs. The wireless is going to use that first segment. Employees will be on the second segment. And the third will be on the owner, or I guess CEO segment. So depending on how you want to design your network, you can isolate it to where they can't talk to each other. Or you could leave it open. You can allow them to. Okay, so we already discussed how to do the 128 division method. I think it's excellent. You should practice it out as much as you can. Let's say that we need to use this same address again, but we're going to use a CIDR 27. And I want to build, let's say, 6 subnets. How would you design that? If you want extra practice, you can do this on your own. But this gives you an idea. You can just start giving yourself questions like this in designing random networks. Try doing a class A, a class B, a class C. Start doing things that are not of the ordinary, like 192. Start doing 202. We'll try to have fun with that. You can do some different practice questions on the internet. I won't make this whole video about subnetting, but it is an interesting topic that takes quite a bit of practice, but it's fun once you got it down. Okay, so moving on. You don't have to use numbers in order. You could use any kind of numbers you want to. You don't have to use a default gateway of .1. You don't have to always use a network ID of 0. But generally there is organization to this. You might need to work with other people who will help you design the network or maintain it. And it's just better to follow best practices. So what are the best practices? Give the default gateway the first or last IP address in the network. We do this in my organization. We use the last address available as the gateway. Okay, use the remaining IP addresses in sequential order. So go in order, don't go so randomly. Use blocks as they're assigned. Okay, try to separate servers from clients. So you don't want to have all of the same IP addresses mixed up. Let's say you want this block to be servers, you want this block to be your clients, you want this block to be printers, something like that. So that way it's kind of easy to take a guess of what device is on what block. And lastly, you should always document what you do and why you do it if something is non-standardized. So now we have an understanding of a subnet mask that's towards the left of your binary, and then the hosts that are available on the right of your binary. And that's just kind of how binary math works and addressing works, and seems like we got that down. Great. So then how do they get an IP address. We have IP addresses that are available for computers, but how did they get this IP address? Well, there's different ways. The first one we'll talk about is dynamic host control protocol, DHCP server, and DHCP clients. So this server serves these clients. So they ask for an IP address, it confirms and gives it back to them. Okay, so for example, we'll read this comment here. Is there a DHCP server out there? I'm wrestling with tough identity issues and need help. Okay, don't you ever feel that way? Don't you just need a DHCP server to give you your identity? Well, in this case, we do. Hi, I'm your DHCP server. Your IP address will be 12.34.56.78. Your subnet mask will be 255.255.255, and your default gateway will be .1. Do you accept it? So, request DORA, DOAR, discover. Okay, we just discovered. O is offer, so it's going to offer. Request it. Hey, yeah, I would like that. Request and then accept. DORA. DORA is how DHCP packets work. Now that I'm secure with my identity, I can face the cruel world without fear. Thanks, DHCP server. No problem. By the way, you've got those addresses for 5 days. Don't get too comfortable. So you can configure how long you want an address to be assigned to a computer, or how frequently it requests or expires. There's different settings you can control there. Okay, relay. DHCP initial 4-way DORA handshake relies on broadcasting to work with. I was just talking about DORA, right? But what if we don't want that? Look out, DHCP packets coming through, and it stops here. No, they're not. I'm blocking your broadcast address. Hello, is there a DHCP server out there? I can hear you loud and clear. I can offer you. So that's called relay. When you relay out a packet, a broadcast to a computer, and they want it, and they accept it. Okay, you can block broadcast traffic. Sometimes on really big networks, broadcasting can cause problems. That's why you want to break down your networks into certain subnets, and then also VLANs and different topics like that, but that's for a different video. Okay, so we know that it can be dynamic or automatic. There's all kinds of different settings that we can set and how long they're good for. And in most cases, having dynamic addressing is pretty good. It makes your job easier. What if you had to go around to every single computer and assign an address? And what if there was a problem? You had to walk around to each computer or remotely go into it and fix it. That would be a headache. Certain devices don't need as much maintenance, like a printer. Once you set up, it's probably good for a while until a power outage or a factory reset or something funny happened to it. Same thing with the camera, possibly same thing with the server. You can even say an exclusion of addresses that you do or do not want to be in the available pool. So that way, from here, we took 50 addresses out, and we're going to use these 50 addresses for something that's not a DHCP client. Okay, and another point I want to bring up, something that's actually quite popular in the world of IT is the DHCP reservations. So you can reserve an IP address. Maybe you don't want to constantly make that security camera static and have to configure it every time. You wouldn't have to this way. As long as you know the MAC address of the device, that's all you need to do, put in here. So that way, if this camera breaks again and you need to replace it and you don't want to configure it, you can just put the MAC address of the device here. As long as it finds that MAC address on the network, it will assign it this IP address every time using dynamic host control protocol instead of static. So that's a pretty cool way to configure a network. Makes it easier to upgrade things and less work for network administrators overall, especially once networks start getting very big. Okay, I want to talk about these commands as well. So you're going to need to know ipconfig release. That will release your address, so you have nothing. Your adapter, your interface will be 0. And if you renew it, that will pull a new IP address from the DHCP server. Here are the same commands, but using ifconfig. So in Linux, you would need to specify the adapter, Ethernet 0, and tell it to go off, go down, right? So it has nothing, and then come back up. And when it comes back up, if it's set to use DHCP, then it will grab that new address. Same thing here. DH client is for Mac. You can set it to release, so it has nothing, or it's a down, right? R for release. And then once you run the command again, it gets a new address. So this will force DHCP to do a discovery and offer request and accept again. And you can use this for troubleshooting. Pretty useful when you suspect that DHCP is a problem on your network. Okay, there is a security part of this, so sometimes funny things do happen. There might be a rogue DHCP server by accident or by purpose. So sometimes maybe an unknowing user brings a router from their home because they need to plug in something, or maybe they want to make a wireless network of their own and they think that's a good idea. But if they already have a DHCP server out there, it may cause conflicts on your network. You may not be able to access the same network resources. It may cut off, a different subnet mask, and it's going to create problems. And that's an innocent way, but a more less benign way, maybe some attacker or someone inside the networks trying to become the DHCP server and gather information and do malicious things. So you have to be aware of that and how to resolve that quickly, and I try to identify it quickly on network, or else it's going to wreak havoc and make computers not work correctly. And you made it to the end. Good. So usually we do a pop quiz. So let's read them. Number 1, change the coffee shop subnet. We had a coffee shop and the different 3 subnets, and I wanted you to make 6. Did you do that? We can practice it. Okay. 2, convert binary to an octet. You absolutely need to know how to do that for the Network Plus. And 3, which of these addresses are not valid? Okay, so let's do number 1. I wanted you to break down these different subnets, right, in these blocks on the address and what's available. We pulled 3. Why don't you make it, a block 26 or 27, or maybe move it around and just play with it and quiz yourself. I think this is a good example. This is a good place for you to start. Maybe you could design out a network and then test it at home. Set up your router to be like this, or set up some other equipment to use these blocks and see if it works. So I'll let you do that on your own. Have fun. It's a process. Okay. Change binary to IP. Here we have, what is the result of converting 192.168.0.1 to binary? So we know already this address. We wrote it out before, so this should be pretty easy then. Process of elimination. Dude, D looks totally different from the other ones. Nope. C doesn't have any zeros on the last octet. Okay, now it's 50-50, right? Well, here we have a 0 or we have a 1. Well, that's not a 0, right? That's a 1. It has to be A. We've written out 192 before. We know this is 128 and this is 64. Yeah, that's 192. We know that these numbers in these positions is 168. We've done that math already. So that's pretty cool. You're going to see a question like that on the exam or have to do this in some way, and you will score higher if you feel confident. Okay, which of these addresses are not valid? We have these different CIDR blocks, and you should know right off the bat which of these are, private or class A or B or C, and which one is not correct. And here the answer is B. We cannot use a loopback. 127 is for your local loopback connection for testing, and you cannot use that for networking. So the answer is B. Well, did you learn something new? Did you gain confidence? Well, thank you for watching, and have a good one.